Hello everyone, so welcome back to my channel. Today we're going to go over this problem of fluid mechanics. So a belt which is driven by drive cylinders having a radius of 10 centimeter running at a constant rotational speed of 60 RPM is suddenly placed against the surface of a lake, as shown in the following figure. The distance between the drive cylinder centers is 2 meters and the width of the belt into the page is 0.3 meters. The lake temperature is 10 degrees Celsius. The horizontal speed of the water u decreases with distance from the belt according to u is equal to capital U times 1 minus the error functions of y over the square root of 4vt, where u is the speed of the belt, y is the distance from the belt, v is the water's kinematic viscosity, and t is the time starting from when the belt first touches the water. The function ERF is known as the error function. So estimate the power required to drive the belt at a time of t equals 1 second. And b, what is the total energy used to drive the belt after 10 seconds? So before beginning this problem, we have to understand what power means. So what power is power is equal to work over time. It has units of joules per second. And work is usually expressed as force times distance. And we can express power thus as in unit analysis or simple terms, force times d over t. And d over t is actually v. So power is actually equal to force times v. Now over here, what is the force going to be? It's actually going to be a shear force um, from shear stress. And shear stress, so shear force is going to be shear stress times area. So our general form for power we now have is equal to tau times A times V, which is velocity, and A is area, and tau is shear force. This is the general form. Now we have to decide where each of these values come from. So in a Newtonian fluid, as we just discovered in a previous video, Newtonian fluids include air, water, and alcohol and other things. But Newtonian fluids general just means um that the shear stress is directly proportional to the rate of, I think, strain. So in other words, for Newtonian fluids, tau, the shear stress, is equal to mu times du over dy. And this is known as um the gradient. But mu is known as the kinematic viscosity. So over here it's equal to actually v times du over dy. Hello everyone. So we're going to continue with the differentiation. So basically du dy is going to be equal to as they included basically they gave us uh the derivative of the error function already in the Wikipedia. So from the Wikipedia page, we have that the derivative of the error function is equal to 2 over root pi times e to the negative z squared. So du over dy is going to be equal to uh okay, let me write this again. So d u 1 minus ERF of y over square root of 4vt. And with respect to dy. Now this is a very, very complicated um derivative, or not very complicated, but pretty complicated. So we will have derivative of u with respect to y is going to be equal to 0 since it's a constant. And also we have derivative of u times ERF times y. ERF of y over root 4 vt. So negative d of ERF y over square root of 4 vt over dy. Um, Basically, by the chain rule, we have to apply the chain rule here, so it's going to be equal to negative 2 over root pi times e to the negative y over root 4 vt squared, and then times the derivative of this whole thing. So times dy over root 4 vt over dy. Yes. And then this simplifies to negative 2 over root pi times e to the negative y over square root of 4 vt squared times uh times 1 over root 4 RT, I believe. And basically the shear force is gonna be at this distance, which is at y equals 0, because that is the shear force that is in contact with the belt. So we actually evaluate this at y equals 0. And this will give us evaluated at y equals 0. We plug in 0 for y. So it gives us negative 2 over root pi times e to the negative 0 squared, which is e to the negative 0, which is going to be simply 1, and multiplied by 1 over square root of 4 RT. So that is equal to our du dy at y equals 0. Oh, and here I actually forgot something. We actually have distributed the u into the error function. So we just have to multiply this whole thing by u. So we can just add a u over here and u over here and u over here. And just so we don't lose track of the big picture, this is equal to du dy evaluated at y equals 0. So now we have all that underway. We want to find the value for the shear stress. So tau is equal to the kinematic viscosity, which in this case is represented by V, times du dy, which is which is the -2 over root pi mm, times u over square root of 4RT. And thus, the shear stress is equal to that. Now, the shear force is going to be tau times A. And A is going to be the area of the belt that is in contact with the water. Ah. Yeah, so shear force equals tau times A belt. So what is the area of the belt? The area of the belt is going to be, it says it has a depth of 0.3 meters into the page, so it's actually going to be 2 meters times 0.3 meters. So it's going to be a belt equals 0.3 meters times 2 equals 0.6 meters. Yeah, so then this will be equal to V times -2u over square root of 4 pi RT multiplied by the area of the belt, which is, sorry, 0.6 meters squared. And as we mentioned before, power is equal to tau A times the speed. So power is equal to tau times A belt. Times the speed, which is actually u. The u over here is from this. U is the speed of the belt. So then this is equal to -0.3 u v over root 4 pi RT times u. So we can actually just put it over u squared. So let's see which quantities are known. So we can find V, the kinematic viscosity of water, from the internet. What about U? We don't know U yet. What about R? We hold on. So what is R actually? Okay, so sorry, that is actually not R. This is actually V. I confused myself because the V looks so much like an R due to how I wrote it. But if you want, it's a V. So that certainly makes matters more simple because we have a V over here as well. And we can now plug in known values. So also t is going to be 1 second. So what is u going to be? Well, u is the belt speed, and it can be related to the rotational velocity of the wheel. So the wheel spins at 60 RPM, and it's going to have a tangential speed over here of u. And u is going to be related to the RPM by omega times r, where r is the radius of the drive cylinder, which is 10 cm. Basically, omega is equal to 60 RPM, which is equal to 60 rotations per minute times 1 minute, 60 seconds, um, times 1 rotation, uh, 2 pi radians, and this is equal to 6.28 radians per second. So r is the radius, and it's equal to um 0.1 meters because it's 10 centimeters. So 0.1 meter. Yes. And thus we are going to have omega r is equal to u. So u equals omega r equals 6.28 times 0.1, and it's equal to 0.628 meter per second. We now have to find the dynamic viscosity of water. So the kinematic viscosity of water at 10 degrees Celsius is approximately 1.306 times 10 to the negative 6 meters squared per second. So that is the value we're going to be using, actually, for the kinematic viscosity. So here we know that kinematic viscosity is equal to 1.306 times 10 to the negative 6 meters squared per second, I believe. Now it is finally time to plug in all known values. So the power is equal to negative 0.3 times 0.628 squared times 1.306 times 10 to the negative 6. Okay. And all this over square root of 4 pi times 1.306 times 10 to the negative 6. And then t is just 1 second. So hopefully that will give us the right answer. Let me calculate it quickly. Actually, in this problem, I made a major mistake, and I'm sorry for the confusion. Um, basically, dynamic viscosity and kinematic viscosity are totally different. And mu represents dynamic viscosity, while V represents kinematic viscosity, which is totally different. So these two quantities are not equal. So we cannot set them equal to each other. And actually, because of that, um, yes, we can evaluate du dy the way we evaluated it, and the equation we got was correct, but the equation for tau is therefore incorrect and needs some revision. So we tau instead of kinematic viscosity, we use dynamic viscosity, which is mu. And so F here is equal to tau times A vel, which is equal to mu times that. And we now have 0.3 times u squared, yeah. But times mu, over here it's mu. And yes, the rotational angle, angular velocity to linear velocity is correct. R is equal to 0.1 meters, U is equal to that, which is still correct. However, over here we will actually need to find the yes. Do they give us the yes, they also don't give us the kinematic viscosity of water, so we're gonna need that as well. And we're also going to need the dynamic viscosity of water. So the dynamic viscosity of water at 10 degrees Celsius is approximately 1.306 millipascals second. So 1.306 times 10 to the negative 3 Pascal second. So 1.306 times 10 to the negative 3. Um, basically Pascal second. And thus we can plug in our new values. So it will be negative 0.3 times 0.628 squared times mu, which is okay, times 10 to the negative 3 over 4 pi times that, okay, times 1s. Let's calculate this out again. Another error I made was in this step. Actually, it's 0.6 times 2. So I should be negative 1.2 because we have 2 times 0.6. Sorry for all the careless mistakes. Yes, and I think that corrects it all. Let's calculate it again. And at last, we have our answer, which is negative 0.152. Or wait, actually it rounds to 3 because it's 0.15256. So it rounds to 0.153 watts. However, it's the power required to drive the bell at a time of t equals 1 second. So in magnitude, this is 0.153 watts. Now, let's solve part B. What is the total energy used to drive the bell after 10 seconds? This is now easy because energy E is equal to the integral of the power over times dt, where t is a differential time, and t is from 0 to 10 seconds. And also, there was something I wanted to go over briefly, that is the relationship between the dynamic viscosity mu and the kinematic viscosity v. So these are related by density, as you see over here. 1000 is the density of water. An interesting fact. So, basically, an alternative expression for F shear is equal to well, mu times negative 2u over root 4 pi vt times the area, which we can leave as a. And we're actually going to use this equation and integrate it. This is the equation we're going to be integrating down here. Also, don't forget the little u in the power equation. Uh, People often forget that, so we actually have u squared down here. So integrating this, we can actually factor out several terms. We can factor out 2 u squared mu over 2 square root of pi times v, and then and also an a. And this leaves us with the integral from 0 to 10 of 1 over root t dt. This is equal to negative uh negative u squared mu a over root pi v, and then integral of 1 over square root of t is equal to negative 1/2 times t to the negative 1/2 minus 1, which is negative 3 over 2. This evaluated from 0 to 10. Actually, I think this one is wrong. It's actually supposed to be square root of t. Because square root of t, when you differentiate it, you have 1/2 and then t to the negative 1/2 power. But we have to multiply it by a 2 because when we differentiate square root of t, we're gonna have an additional coefficient of 1/2. So basically, we have negative, but we want the magnitude, so the answer is 0.963 joules. And this is from just plugging in all our known values in for the equation. So 10 for t, 0.2 times 0 gives us the 0.6 meters squared. Uh, the dynamic the uh the dynamic viscosity is 1.3 times 10 to the negative 3. And we also have u squared and all the other values. So thank you for watching this video. This is the end of the video, and I hope this problem was helpful to you guys in gaining a better understanding. Here's a quick scroll through. Why does our answer 0.966 does not match? Here's another method of solving for the energy. It looks like they got a slightly different answer, but it's okay. Yeah. So I'll be posting these slides. Bye.